Welcome back, everyone, to the Deep Dive. Today, we're going to be diving deep into a paper. Let me see. Yeah, it's called RETSTA. That stands for Redinal Report Standardizing Assistant.
Yeah.
And it's all about, standardizing clinical reports about images of the fundus, which is the back of the eye.
Right.
And, that might not sound super exciting at first, but it's actually a pretty big deal in healthcare. I mean, having clear, consistent information in those reports, super important, right? For so many reasons. Like, first off, you want to make sure everyone's on the same page when it comes to patient care.
Exactly. Yeah.
And, then you got to think about sharing data between different doctors, different hospitals, research, all of that.
Yeah, absolutely. Without standardized reports, it's like, yeah, like trying to put together a puzzle with pieces from different sets.
Exactly. It just doesn't fit.
Right.
And, these standardized reports, they're kind of like the foundation for all those electronic health records we hear so much about. They make it possible to actually do research, to analyze data across a bunch of different places.
Right.
But the thing is, with these fundus image reports, there's a lot of variation. Like different doctors might describe the same thing in totally different ways.
Yeah, I've seen that. Like different formats, different, styles of writing.
And even different terms for the same condition.
Exactly. And that makes it really tough to understand the data, especially for things like,
Oh, yeah, for those big fancy LLMs.
The large language models that are trying to learn from this data.
Right. And that's where this RETTA comes in. This paper basically says, hey, we can use LLMs to tackle this standardization problem.
Yep.
And they're not just talking about English reports either.
No.
They've actually built this system to work with both English and Chinese.
That's huge, yeah.
So they created these two models, RETSTA-7B0 and RETSTA-7B. And get this, RETSTA-7B is the first one to actually achieve report-level standardization.
Wow. Okay.
And it does it better than any other LLM out there.
Really? Even across both languages?
Yep, even across both languages.
Yes, really impressive.
It is. So, you see, this isn't just about making the reports look pretty.
Yeah, no.
It's about unlocking all this clinical data.
Yeah, making it usable for research, for AI development.
Exactly. It's about making the data actually mean something.
Right. And, thinking about the history of medical reporting, it's really fascinating how we got here. I mean, for so long, doctors just kind of did their own thing.
Right.
Which made sense in a way. It allowed for a lot of nuance in their descriptions. But when you try to put all that data together, it becomes a real nightmare.
It does.
So for a long time, people in medical informatics, they've been trying to figure out how to standardize this stuff. They've tried all sorts of rule-based systems, controlled vocabularies, all that. But it's tough. Clinical language is so complex.
Oh, yeah, it is.
So then these LLMs come along.
Right.
And suddenly there's this whole new way of thinking about it.
Totally.
Because these LLMs, they can actually understand and generate human language in a way that we've never seen before.
Right.
So, this paper, it's really building on all that progress, specifically focusing on ophthalmology. Which, as we said, has all its own unique terms and phrases.
Right.
So the development of RETSTA is a pretty big step forward. It shows how we can use these powerful LLMs to make healthcare documentation way more consistent.
Okay, so let's break down how they actually did it.
All right.
First things first, they had to create this, what they call a bilingual standard terminology.
Okay.
For describing everything you see in those fundus images.
Yeah, that makes sense. You need a common language.
Right. But they didn't just make up a bunch of words randomly.
No, of course not.
They actually started with these really well-established medical vocabulary. Like the big names. ICD-11, which classifies diseases.
Right, yeah.
The preferred practice patterns from the American Academy of Ophthalmology. Which basically tells doctors how to do things.
Right.
And SNOMED and CT.
Okay.
That one's like a super comprehensive clinical terminology system.
Yeah, I've heard of that one. It's got everything.
Yeah. Diseases, symptoms, examination findings, you name it, it's in there.
Makes sense. So that gave them a good solid base.
Exactly. A strong, standardized core. But here's where it gets interesting. They realized that these formal systems, they don't always capture the nitty-gritty details.
Oh, yeah.
Like the way doctors actually describe things in their reports.
Right, like the everyday language they use.
Right. So what do? They took a huge data set, almost 500,000 real fundus diagnostic reports.
Yeah, That's a lot.
It is. And they basically went through them all and pulled out all those frequently used phrases.
Oh, I see. So they're capturing the way ophthalmologists actually talk and write.
Yeah, exactly. Like their unique style,
That's really smart.
And then they took all those terms, all those phrases, and they put them through a super rigorous process.
Okay.
They used computer rules to match stuff up automatically. But then they had a senior ophthalmologist manually check everything.
Oh, wow. So they didn't just trust the computer.
Nope. They had to make sure everything was accurate, clear, clinically relevant.
Yeah.
No duplicates, no misleading terms.
So it was like a double check system.
Right. And in the end, they had a super polished list of 362 standardized terms.
Okay.
In both English and Chinese.
Very cool. So they really laid the groundwork for global understanding.
Yeah, exactly. No more language barriers.
I mean, that's what's so important about this terminology, right? It's not just the standard medical codes.
Yeah.
They added in those phrases that doctors actually use.
Right.
So the whole thing is way more aligned with real world practice.
Makes it more useful.
Yeah.
Right?
Oh, absolutely. And having that expert review, that's essential. It makes sure the terms are accurate and practical.
Right. Not just some theoretical mumbo jumbo.
Exactly. It's got to actually work in the clinic.
Totally. Okay, so now we've got our standardized language. Time to build the AI.
Right. The models.
Yeah. So they started with this model called RETSTA-7B0.
Okay.
And that 7B, that just means it has like 7 billion parameters.
Right. So it's not one of those super massive models.
No, not really. Especially by today's standards. And that 0, well, that kind of hints at a big challenge they faced.
Okay.
Getting enough data to actually train the AI.
Yeah, I can imagine that being tough.
It is. Because think about it.
Okay, yeah.
You need examples of those messy original reports paired up with the perfectly standardized ones.
Right. You need that before and after to train it.
Yeah. And that kind of data. It's not just lying around.
Makes sense.
So they had to get creative. They started by making their own data set.
Oh, wow. Okay.
4,000 pairs.
Okay.
2,000 for testing, 2,000 for training.
Got it. But that's still not a ton of data.
No, not really. So they used this cool trick called data augmentation.
Ah, interesting.
Basically, they took that small data set and they artificially expanded it to 10,000 pairs.
Okay.
By mimicking all the little quirks and errors you see in real reports.
Oh, I see. Like typos and stuff.
Yeah. Typos, missing punctuation, ambiguous phrases, negations, like when doctors say no evidence of.
Right, right.
They trained it on all of that.
Wow. So they basically threw everything the model might encounter in the real world at it.
Yeah, pretty much. So they use things like syntactic noise injection, semantic perturbation, where they add in negation words or change the probability, and synonym replacement, swapping out words for similar ones.
So they really put it through the ringer.
They did.
Yeah.
And this was super smart because it forces the model to be robust.
Right. It can't just rely on perfectly clean data.
Exactly. And that's a big takeaway for anyone working with clinical data.
Yeah, for sure. It's messy out there.
It is. Okay, so once they had this augmented data set, they used something called LoRA, low rank adaptation, to fine-tune a pre-trained LLM called Quen 2.57B instruct.
Got it. And what's LoRA exactly?
Well, think of it like this. You have this big, complex LLM.
Okay.
You don't want to retrain the whole thing from scratch.
Right. That would take forever.
It would. So LoRA lets you just tweak certain parts of it.
Oh, I see. So it's like fine-tuning a guitar instead of building a new one.
Yeah, that's a good way to put it.
So it's way more efficient.
Right. And that's how they created RETSTA-7B0.
Okay.
That's the first model.
Got it.
Now, the second model, RETSTA-7B, they took things even further.
Okay. How so?
They used RETSTA-7B0, the first one, to process a way bigger data set.
Oh, wow.
60,000 original reports.
Okay.
And they used it to generate a bunch of candid, standardized reports.
So they used the first model to make more data for the second model.
Exactly. But they didn't just trust everything it spit out.
No, of course not.
They had this rule-based filtering system to catch any errors. Like logical conflicts, incorrect terms.
Right.
They also looked at how similar the generated reports were to each other.
Interesting.
And they removed some of the really similar ones.
Why'd they do that?
So they could get a wider range of conditions represented.
Oh, that makes sense.
Now remember, the original data set was in Chinese.
Yeah.
So they used another LLM, this one called DeepSeek V3, to translate everything into English.
Oh, wow. So they really went all out with the LLMs here.
They did, but they were careful.
Okay.
They made sure the medical terminology was translated accurately.
Right. You don't want to introduce any errors in the translation.
Exactly. So in the end, they had this massive bilingual data set.
Okay.
Over 60,000 pairs.
Wow.
And they took that same base model, Quinn 2.57B Instruct, used LoRa again, and fine-tuned it on this huge data set.
Right.
And that's how they created RETSTA-7B.
Got it. The final model.
Yep, the big one.
And this approach, using the first model to generate data for the second is pretty clever.
It is. It's like they're bootstrapping the whole process.
Yeah. It's like, teaching a student the basics so they can then go on and learn the advanced stuff.
Yeah, that's a really good analogy.
And the fact that they included that translation step and made sure the terminology was consistent, that shows how important it is to handle multilingual data properly.
It does. It's not just about slapping on a translation and calling it a day.
No, you got to be careful.
Okay, so how did it actually perform?
Yeah, let's get to the results.
Well, they did a bunch of comparisons.
Okay.
Tested RETSTA-7B against other LLMs, including some designed for medical stuff, and some were even bigger, more parameters.
Right.
They used a separate set of reports for testing.
Okay.
In both English and Chinese.
Got it.
And they used all those standard metrics for evaluating LLMs.
Yeah, like BLEU and RS.
Exactly.
Right.
RETSTA-7B came out on top.
Oh, wow. That's great.
It is. But here's the interesting part.
Okay.
Those medical-specific LLMs didn't do as well.
Even though they have all that medical knowledge.
Yeah, which suggests that just knowing the medicine isn't enough.
Right. It's got to understand the specific way these reports are written.
Totally. It's got to understand the structure, the language, all of it.
The nuances.
Yes.
Yes.
The nuances. That's the key word.
So it's really about domain expertise.
Yeah, it is. And they also found that the base model they used, Quinn 2.57B Instruct, sometimes put Chinese words into the English responses.
Oh, that's interesting.
Yeah, which messed up its scores on the English tests.
Makes sense.
But even with all that, RETSTA-7B was the best.
Impressive.
It is. And they emphasize that, even though it's a relatively small model, only 7 billion parameters.
Right.
Their approach was super effective.
It really worked. And remember that first model?
RETSTA-7B0.
Yeah. The one they trained on that smaller augmented data set?
Yeah.
That one also did really well.
It did, which means those data creation and augmentation strategies, super valuable.
Yeah.
And cost efficient.
That's always good to hear.
It is. But the big performance jump from RETSTA-7B0 to RETSTA-7B, that really shows you the power of having that massive bilingual data set.
It does. More data, better results.
Pretty much.
Seems like a classic machine learning lesson.
It is. And the last thing they did was some tests to make sure the English translations didn't mess up the model's ability to process Chinese and vice versa. And it all worked out.
So it can handle both languages without any problems.
Yep. No interference.
That's amazing.
It is. So yeah, these results really back up their approach.
They do.
It shows that even a small model can outperform the big guys.
Yeah, if it's trained the right way.
Right. With the right data, the right methods.
Domain expertise.
Domain expertise. Exactly.
And that success with the data augmentation, that's a big deal too. It shows us a way to deal with the data scarcity problem in specialized areas.
It does. It's like you don't always need tons and tons of data.
Right.
If you're smart about how you use it.
Exactly.
And the bilingual capabilities.
Yeah.
That opens up a whole world of possibilities for cross-lingual research and collaboration.
It does. I mean, imagine being able to analyze medical data from all over the world.
That's the dream. Okay, so to wrap up, the big takeaways here are, first, they created this awesome bilingual standard terminology for the Fundus, a super valuable resource.
Totally.
And then they built these two awesome LLMs, RETSTA-7B0 and RETSTA-7B.
Right.
Which proved that you can standardize these reports in both English and Chinese.
And do it really well.
Really well.
Yeah.
And, the researchers are already talking about what's next.
Yeah, what are they thinking?
Well, they want to use RETSTA-7B for other tasks.
Okay.
Like building AI that can understand both images and text.
Oh, that's cool.
It is. And they're also exploring whether this whole approach can be applied to other medical specialties.
So this could be just the beginning.
It could be. And that brings us to our final segment, novel notions.
Yeah, time to get speculative.
Exactly. Time to think big. So, reading this paper, it really got me thinking.
About
About whether this whole RETSTA strategy could be used in other areas of medicine.
Oh, yeah.
Like we talked about radiology, right? They have DICOM for the images, but the reports, they're still all over the place.
Right, yeah.
And pathology, too.
Mm-hmm.
SNOMED CT is great for naming diseases, but the descriptions in those reports can be super varied.
Totally.
So what if we could build these bilingual terminologies for other fields?
Okay, yeah.
Using the same approach they use here.
So draw on existing guidelines, collect a ton of real-world reports.
Exactly. And then use data augmentation techniques that are tailored to the specific problems you see in those reports.
Right, like each specialty has its own quirks.
It does. And then we could fine-tune LLMs, just like RETSTA, to standardize everything.
Oh, wow. So we could have like a RETSTA for radiology.
Yeah, and a RETSTA for pathology.
And cardiology and neurology and...
It's like the possibilities are endless.
They are. I mean, if this worked, it would be huge.
It would. It would completely change how healthcare systems share information.
Yeah.
And it would make large-scale research so much easier.
Right, you could compare data from anywhere.
Exactly. And it would pave the way for better AI diagnostic tools.
Oh, for sure.
Yeah.
Because the AI would be trained on this massive standardized data set.
Right. It's so exciting to think about.
It is. And, you know, building on that, another cool idea is what if we could integrate a future version of RETSTA directly into the clinical workflow?
Oh, like in real time?
Yeah. Like, imagine an ophthalmologist is examining a patient. They're dictating their findings. And there's this AI powered by, like, RETSTA 2.0 or something. And it's listening.
Okay.
And it's giving feedback.
Like as the doctor is talking.
Yeah. Like, hey, that phrase you just used, it's not in the standard terminology. Maybe try this instead.
Whoa. That would be wild.
It would. It would be like having a standardization expert right there in the room.
So it would catch inconsistencies before the report is even finished.
Exactly. Proactive quality control.
I love it.
Of course it would be a technical challenge.
Yeah, I can imagine.
You'd need some serious real-time processing power. And it would have to integrate seamlessly with all the electronic health record systems.
Right. Yeah, that's a big one.
But if we could pull it off.
Oh, it would be game-changing.
Totally. It would make clinical data so much clearer, so much more consistent.
It would. Both for immediate patient care and for future research.
Yeah, the data set would be gold.
It would. Okay, so obviously these are just ideas.
Yeah, for now.
But it's exciting to see how this work on standardizing medical language could lead to even bigger things.
It is. It really shows the potential of LLMs in healthcare.
It does. All right, so that wraps up our deep dive into RETSTA.
Thanks for taking us through it.
No problem. It's a fascinating one. And as always, if you want to check out the paper itself, you can find a link in the description.
Don't forget to subscribe and leave a comment below.
We'll be back next time with another look at cutting-edge research. See you then.